Hey everybody, we're going to talk about mechanical waves today, specifically transverse waves, longitudinal waves. We'll talk about the different parts of those waves and so on, and then we'll explain these equations, what these quantities stand for, and what the relationships are. First of all, let's deal with a wave. What is a wave? Well, it's when energy moves with no net transport of matter. Now, here's what I mean by that. If I were to take an object and throw it, here's like a baseball being thrown. If I throw this ball, it's got kinetic energy, doesn't it? And it's carrying the energy with it. So I did work on it over here, and it transports the energy. It moves the energy to a different place. But in the process of doing that, the baseball actually moved from here to over here, right? So there was a net transport of matter. That's what we mean by net transport of matter. The matter got moved. But there are these things called waves where energy gets moved, but matter doesn't. It pretty much, it stays where it is. For example, look at this slinky. And let me zoom all the way out. Zoom all the way out. I got the slinky right here. And if I want to move energy from my right hand over to my left hand, I can do it by producing a wave. Okay, so what I did is I moved the material up and down, and it moved through the slinky, and it could be a rope, it can be air, it can be just about any kind of material. The wave moves through it, but notice that the slinky stays where it is. I mean, it goes up and down a little bit, but it always ends up back where it started. So there's no net transport of matter, but the energy did move through the material. In fact, you can see the energy bouncing back and forth. Okay, so let's see a little bit again. Okay, so now there are different kind of waves. There are waves that we call electromagnetic waves. That's light and radio and all that kind of stuff. And it obeys these equations right here. But they don't require any matter at all. They don't require any kind of material to move through. The energy doesn't move through a material. It moves through empty space as an interaction between electric and magnetic fields. But if you have material, you can move the energy through that material, and that material is called a medium. That's a word you should know. Medium is the material the wave energy is moving through. Okay. So, now in this case, I mean, in my demonstration, the wave was a slinky, and I like slinkies. It's fun to show energy moving through them. And when we get back from spring break, I got a bunch of slinkies that we'll play with. So that's a slinky wave of material. Now you're hearing me right now because of sound waves. That's the energy moving through air. Okay, and then there's water waves, and if you fling a rope back and forth, you can have transverse waves like that. So let's talk about what transverse waves are. This is pretty easy stuff today. I think it's good to end the week before spring break with this kind of stuff. Okay, so here's my material. Maybe it's a rope, or could be a slinky. If I make it, I'll make it a long slinky like this. Or it can be just about anything. any kind of material. It can even be the ground during an earthquake. And what I'm going to do is I'm going to take this is my medium, and what I'm going to do is I'm going to disturb the medium by sending a pulse by moving the material up and back down, and then down and back up, and up and back. So I'm just going to move the material up and down like this. And this is easy to demonstrate, but what happens is you get the material, you get a wave that goes through the material like this, right? Looks like a sine wave or a cosine wave. It is a sine wave or a cosine wave sometimes. Okay, and now I can't draw it, I can't draw an animation, but this is moving at a certain speed. Now this right here, the distance from the equilibrium position of my material to its maximum displacement away from there is called the amplitude. Okay, and the amplitude goes from here to here or from here to here. So this is the amplitude. Now the amplitude is not from here to here. That's twice the amplitude, from the minimum to the maximum. Sometimes this is called a crest. Sometimes this is called a trough of the transverse wave. Okay, and it's moving. Well, I'm making a certain number of these per second, right? I mean, I'm going to be sending these pulses through here, and we call that the frequency. The number of pulses I make, F, is equal to the number of, not pulses, but complete waves, number of cycles that I make per second. So if I went 1, 2, 3, well, okay. I'm not going to start this over again. We might get interrupted a couple more times. Okay, sorry about that. Now the period is the number of seconds to make one complete cycle. Okay, so this is like, and one complete cycle is one complete wave. Like you go up, down, and then back up to where you started. That is the time, that is the period. Okay, and so the frequency is equal to 1 over the period. Okay, which we've kind of talked about. Now here's something new that we haven't talked about, and that's the wavelength. The wavelength is the distance between repeating parts of the wave. So let's start here. Let's look at the wave right here. Now, here we see the material has a slope like this, and these things are moving that way. But now, where does it repeat that? Does it repeat it right here? No. This is actually half a wavelength. The wavelength is the distance when it starts repeating its motion. And that would be here. See, from here to here. That would be one wavelength. And we have the wave length. And we have a letter for wavelength. It's a lambda. Okay, now I'm going to draw it really big right here. A lambda. It looks like a teepee or an upside down lowercase y. You kind of make a thing like this and you put a little hat on it like that. That's a lambda, and lambda is the wavelength, and it's meters per wave. It's measured in meters per wave or meters per cycle, or how far is it between repeating parts of the wave. Now I went from here to here, but you could easily go from trough to trough. This would be the wavelength, or crest to crest. That would be the wavelength. I mean, it's all going to be the same, no matter where you measure from. If this is a repeating part of the wave, and it's a good standing wave or good wave, constant frequency, constant speed, then the wavelength will be constant. Okay, now let's talk about so we got the different parts of the wave. We've got a crest and trough, amplitude, velocity, frequency, period, and now we have wavelength. Okay, now we need to know the relationship between those. Look, and I'm just going to give this to you so you can get started. I don't want this to be a long lecture like I usually do. Sorry about that. So V, now the velocity of the wave. Well, think about it this way. How long is each wave? Well, that's the wavelength, isn't it? And how many waves go by each second? Well, that's the frequency. So this is how many waves I make every second, and this is, or you can also think of it as how many waves go by each second, and this is how long or what the distance is between each wave. And this gives you the velocity. Let's take a look at units here. This is in hertz, or you can think of it as waves or cycles per second. And what is lambda? Lambda is the wavelength. So this is the meters per wave. And notice that goes away and you get meters per second. And that's the speed of the wave. Velocity equals frequency times wavelength. But since the period of the wave, the time to make one wave, is 1 over the frequency, you can say that this is also equal to the wavelength divided by the period. And this is meters per wave, and this is seconds per wave. So the per wave goes away and you get meters per second. So there you go. So I think, so that is transverse wave, and you'll have some problems where you'll have to draw them, and you'll have to solve some simple problems that involve this. No. Okay. The next thing I've got is that we're going to talk about real quick is longitudinal waves. In longitudinal waves, it's really easy to show with a slinky. So let's draw a slinky like this. And here's the slinky in the relaxed position. We're not making any waves. Don't make waves. Okay, but now what we're going to do is we're going to take that slinky, we're going to grab it, and we're going to move it back and forth like this. So here's the relaxed position, but here's our amplitude this way, and then we're going to pull it back this way, and then we're going to go back and forth. So we're just going to take that slinky and we're going to go like this. Well, what's that going to do? Well, you're going to have compressions and expansions and compressions and expansions and compressions and expansions. So we're going to call this a compression. And this is an expansion. And they're going to move at a certain velocity. Okay. And now the only thing that's different, I mean, all the math is the same. This velocity equals frequency times wavelength works for longitudinal waves as well as transverse waves. I mean, the only difference between a transverse wave and a longitudinal wave is in a transverse wave, you go perpendicular to the direction of the velocity of the wave. Like the wave here is moving to the right, but I'm disturbing it by going up and down, which is perpendicular. But here, I move the material in the same direction. So here the velocity is to the right, and I move the material parallel to the velocity, not perpendicular. And that makes a longitudinal wave. And so here's a little slinky. And and I'm going to send a longitudinal wave through it. Can't really see it that well under the camera, but you can tell, you can see my hand, the way my hand is moving back and forth, and that's sending little compressions or expansions that move through the material. And just wait till after, spring break, and we'll go over this again. So, and so you just apply the same, we just apply the same mathematics to longitudinal waves as we do to mechanical wave, or transverse waves. And I'll ask you to draw pictures of them. I'll ask you to, to solve simple problems. They'll be really easy. One thing about amplitude, and this is just qualitative, the greater the amplitude, the more energy is in the wave. So for both transverse and longitudinal waves, the greater the amplitude, the more energy. The more energy. Oh, also the greater the frequency. The greater the frequency, the greater the energy that's being transported from one place to the other. And this makes sense, right? I mean, if I take my slinky out like this, and I'm going to make transverse waves, if I have little tiny amplitudes, it doesn't take much energy to do that. But if I have big amplitudes, lots of energy. Same thing with longitudinal waves, little tiny. And then if I keep the amplitude the same, but I slow down the frequency, slow frequency, not much energy. High frequency, lots of energy. All right, sorry. Anyway, that should get you through most of what you're going to have to do on the homework. So that is, say it. That wasn't good enough. That is awesome. Have a good spring break.